Hi guys, in our previous video we had been exploring how we solve exponential equations, and in this video we're going to take a look at then how we solve logarithmic equations. And so first things first, if you look at say this logarithmic equation right here, we can see we have log base 3 of x plus 1 is equal to log base 3 of 2x. So the first question I have is just what makes this a logarithmic equation in the first place, and we say that it is any equation of the form log base b of x equals, we'll just throw a c over here where b and c are these constants, but our unknown is inside the argument on the log. And so what we basically want to indicate here is that a logarithmic equation is any equation where the unknown is inside the log. And we're going to give this a name, inside the argument. Okay, the thing that we're taking the log of is typically referred to as an argument. So, if that's the case, then we're going to have to use some properties to help us solve this. So just like we do with exponential equations, we have also a one-to-one property that we can use here, as well as an inverse property. So let's take a look at these really quickly here and make some sense of them. Remember that if two logs are equal and they have the same basis, then the only way this is true is if their arguments are actually equal. So if log base b of x equals log base b of y, well, this is only true if x equals y. So in cases where you have something like, well, I suppose like this, log base 3 of x plus 1 equals log base 3 of 2x, something we could do is immediately we could just go ahead and set x plus 1 equal to 2x and start solving for x. Now our inverse property, a little bit different this time, says if we take b, which is a base of some exponential expression. As a matter of fact, it's the base of this exponent up here. And in this case, you see that the exponent is a logarithm in and of itself. So when you raise an exponential base, or an exponential thing, base b, to the power of a logarithmic thing, base b, what ends up happening is this exponential base and this log base b that we raised it to cancels, and we just get left with the x right here, or in other words, x equals x. And to talk a little bit about why this makes reasonable sense, what I want you to recall is that this is an exponential form. If we rewrite this into logarithmic form, what would it look like? So let me get my log form set up, and I'm going to draw my arrows and everything. But in this case, the base here is b. The base on my log then also has to be b. And we say b to the power of what? Well, over here it said b to the power of log base b of x. So my question is, well, what would this have to equal? If log base b of blank equals log base b of x, well, the only way this would be true is if I had x, okay? So, and that would be this guy right here. B to the power of log base b of x equals x. This is kind of a dumb statement to make, but it's kind of another way of writing the same statement. So it means that if we take an exponential base to the power of a logarithm that has the same base, we're going to make a note here, same basis, then they'll cancel, and we just get the argument inside of our log here. So we're going to take a look at what this might appear like with this property here, one-to-one and inverse properties, and then talk about how we can apply that generally to logarithmic equations. So it says use the properties to help solve the exponential equation for the unknown, and we're still going to list any decimals out to 4 decimal places if proper, okay, or if appropriate. So what we have here is log base 3 of x plus 1 equals log base 3 of 2x. You can see that the one-to-one property certainly does apply here, and so that we can already equate our arguments here, x plus 1 equals 2x. Suppose we'll want to get all of our x's on one side here. And so if I do this, I suppose I get 1 equals just 1x. Hey, here's our solution, x is 1. And again, what I want to emphasize is that, especially with logarithms, we should check our work. Log base 3 of 1 plus 1 should be the same thing as log base 3 of 2 times 1, which means we get log base 3 of 2 equals log base 3 of 2. And that actually works, okay? So our one-to-one property, oh man, that's slick. But let me tell you, it's not always written so that you have a log equal to another log and they have the same exact basis. So let's take a look at our method 2, our inverse property. And the way this is going to look is a little bit different. We say log base 3 of x plus 1 was what we had on the left. On the right, we have log base 3 of 2x. Now, this is going to seem kind of odd, but we're going to use a word here. And actually, I'm going to type this word out just so my handwriting doesn't hinder what you have in your notes. But when we talk about what I'm going to write here, we're going to exponentiate. And that's the word that I want you to write there. Exponentiate both sides of the equation with a base of b. So when we talk about exponentiating both sides of an equation with a base of b, we're kind of twisting the one-to-one property around. But remember that if for any equation, especially exponential, if x equals y, then b to the x also equals b to the y. Or in other words, if b to the x equals b to the y, x equals y. This kind of goes back and forth. So because that's the case, what it means is if two things are equal to begin with, then we can make them both exponents and drop the same bases on them. So this word exponentiate just makes it so we don't have to say we're going to baseify each side, with a base of whatever. We're just going to do this. We're going to take both sides of this equation and we are going to make them themselves some exponents. And what I'm going to do is I'm going to exponentiate both sides with a base of 3. And so the way we read this is, well, if the two things were equal to begin with, then 3 to the power of all this still has to be 3 to the power of all this. But the benefit here is that we can use our inverse property that says an exponential base raised to a power of a logarithm with the same base, those cancel, and what we get left with then is just this. X plus 1 on the left, these cancel over here on the right, and we get 2x. And you see that we kind of arrive at the same conclusion that we arrived at previously, and that our answer would still have to check out. So in terms of the inverse property, I would say that's a more general way of solving this. One-to-one property is always going to be very, 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 very specific. So we're going to take a look at our systematic approach to this. We're going to solve a few equations doing this, and then that's it for this series of videos. But let's go ahead and take a look at our steps to solving logarithmic equations. And this is very similar to exponentials. The very first thing we do is check to see if we can use the one-to-one property. So specifically, we want to rewrite it so that both sides of the equal sign have logarithmic expressions with the same bases. Then set the insides of the arguments of the logs equal and solve for the unknown. Now that's if possible. If not possible, if it's not one-to-one or can't be written that way, then just like in exponentials, we isolated the base of the exponential expression. In a logarithmic equation, we're going to isolate the logarithm. Okay? And then we're going to use the inverse property to quote-unquote undo the logarithmic expression. So I do note here that we do refer to this as exponentiation. But once we exponentiate both sides with a base of b, we're going to solve for the unknown. Now, there is one difference about solving for logarithmic things, and it's this, and I put a little note on here, and it's that sometimes we may need to use the properties of logarithms to condense logs if necessary. And so that just means that sometimes I get an equation like log base b of x plus the log base b of y equals some number over here, n. But to get the log by itself, it's kind of hard to do when you have two logs. So we can use our property that says when we add two logs with the same bases, we really were using our product property here, and we can put it back together, and now we have just one log. Okay, so we may need to use that here. So checking these out. It says solve the following exponential equations. Write any decimal answers out to the first 4 non-zero digits. So looking at this first equation, it looks pretty gnarly. I notice I have log base 2 of 3x minus log base 2 of x plus 1 equals 0. And so my first question is, I'm inclined to ask, could I write this as one-to-one? And actually I recognize that if I add log base 2 of x plus 1 to both sides, log base 2 of x plus 1, what this would look like instead is log base 2 of 3x on the left is equal to a positive log base 2 of x plus 1 on the right. And this is fantastic because it means that I can go ahead and take what's inside my logs then and set them equal to one another, since these are two equal logs that have the same bases. So let's go ahead and finish solving this one here. We get 2x equals 1 if and only if x equals a half. And again, it's worth our trouble of going and plugging this back in up here to check. But in this case, I'm going to go ahead and leave that to the viewer, leave that to you if you want to check it. We're going to move on to letter B. And what I want to consider is, how is this maybe alike or different from the last one we saw? Now in terms of alike, it looks like we have two logs base 5 on the left and they're being subtracted. So maybe what my idea is, I could add this over to the right hand side here. But in this particular case, that wouldn't help because I also have this log base 5 of 3x. So one thing that I'd like for you to do for me, as a matter of fact, is we're going to change this to minus to a plus. I realize that I have a typo here. But what we can do is we can condense these two logs. And because we're adding two logs that have the same basis, we're going to use this property up here that says that if you're adding two logs with the same basis, then we can make this a single log base b where we're multiplying their arguments from the initial two logs. So looking at this, we could condense this into one log base 5, where in the beginning we'll have x times x plus 5. And so we get something that looks like this. And this equals log base 5 of 3x on the right. So what's the benefit to having done this? Well, now I have a log base 5 on the left and a log base 5 on the right. It means that we can go ahead and finish this up by equating these two values. So we can say x plus 5, well, that would have to be the same thing as 3x. And if we work this out here, this is just some polynomial equation now. I suppose we would want to get it set equal to 0. We get x squared plus 2x equals 0. And likely we're going to solve any polynomial equations just by factoring. So I'm going to factor this x plus 2 equals 0 if and only if x equals 0 and x equals negative 2 here. Okay. So in this particular case, I do want to point this out. That negative has really got my attention right here. And when I plug that negative back into the original equation, the very first thing I notice is log base 5 of negative 2, beg your pardon. I'm actually going to stop right there and just say that why can't this work? Well, the reason why it can't work is because we can never take the log of a negative. And that is to say that I cannot say 5 to some power came out to be a negative if my base is positive. So with respect to negative 2 here, I hate to tell you, we went through all this algebraic work and we got negative 2 to work, but it's technically an extraneous solution. When we say extraneous, these are solutions that work out algebraically, but when you plug them back in, fail. Okay. So I'm also going to check 0 in this case, and what I notice is I get log base 5 of 0. I'll actually write out the rest of this just to show all my work here. I don't want you to think I'm cheating you. Equals log base 5 of 3 times 0. And this is also a problem I have here. We can't take the log of 0 because even this part right here, what value would it have? We would say 5 to what power equals 0. There is no power I could raise 5 to and ever get 0. It doesn't work. So with respect to this equation, this is just a good instance of showing you that you know it might work out algebraically, but it doesn't necessarily always work out when you plug them back in. So logarithmic equations, check your answers, and specifically, let's check any specifically negative answers. It's kind of sad to say, but it's not automatically that they fail, but we kind of like they get our attention. Okay, so let's take a look at these on the back here. Starting with letter C, it says log base 3 of x plus 1 equals 2. Now, the first thing I notice is that this is a logarithmic equation, our unknowns inside this log, but I don't also have a log base 3 on the right side. So guess what? 1 to 1 is not going to work. So with respect to the steps that we write here, I'm going to be clear on this. We're going to isolate the logarithm. So what that means is this log right here, log base 3 of x plus 1, there's not like a 2 in front that I would need to divide out of the way. And there's not some loose constant like plus 4 on the left side that I would need to subtract over to the right. This log is already by itself. And so if that is the case, then what we're going to do is we're going to exponentiate both sides, and we're going to use a base that would cause this current base to cancel. So the way this looks is we're going to rewrite this as 3 to the power of everything on the left, log base 3 of x plus 1. And then we're going to say, well, then that's the same thing as 3 to the power of 2. So in other words, we're going to give both sides exponent status, and we're going to give them each a base of 3, because now I know that because of my inverse property, those would cancel on the left. So we get x plus 1 equals 3 squared, or in this case, I'm going to go ahead and evaluate that because it's a reasonable number, and then I'm going to subtract my 1 from both sides. I get x equals 8. And so really quickly here, if I were to check this out, I get log base 3 of 8 plus 1 equals 2. Or in other words, log base 3 of 9 equals 2. That actually works because, I mean, rewriting this in exponential form, we get 3 squared equals 9. That works. Or the other thing I'm checking is also, did I get a negative inside of my log? And I didn't. So I'm not leery that I have to toss out this solution as extraneous. So our only solution here is, in fact, 8. Okay. So letter C compared to letter D. First things first, I want you to understand that there's still only one log here. And secondly, that this log is not missing its base, but this is our common log, or log base 10. So if there's only one log, our job is going to be to work to get that log by itself. And in this case, that just involves us having to, say, subtract 1 from both sides. We would have 3 times the common log of x minus 2 equals 1.75. I then have to divide the 3 out of the way here. And so something I want to say about that is go ahead and leave it as a fraction. We have log of x minus 2 equals 1.75 thirds. Okay. And then the next thing we're going to do is, since we have the log by itself, I'm going to wrap parentheses around both sides, and I'm going to cheat a little bit. We're going to exponentiate both sides with a base of, get this, 10. Remember that our common log has a base of 10. But if I do this, what I'm really going to end up with is, I'll put this up over here, x minus 2 on the left equals 10 to the power of this gnarly fraction here, 1.75 thirds. So the only thing we have left to do is add 2 to both sides. Our final solution, or at least our exact value, is going to be, I suppose, 10 to the power of 1.75 thirds plus 2. And I do want to make sure that, if possible, I can get a decimal for this out to 4 decimal places. So we're going to take a moment to type this one in here. I would have 10 to the power of, now in parentheses, we would have to write 1.75 divided by 3, end parenthesis, and then we're going to take all of this and we're going to add 2 to it. So out to 4 non-zero decimal places, we have about 5.8312. 5.8312-ish, okay, would be approximately our x value there. And it's not negative, so I'm not leery if I plug this back in 5 point something and I put that back in here and I say minus 2, I'm not going to get a negative value inside of my log. Okay, so let's look at these last 3 examples and wrap this up here. Letter E, I notice that I also have only one log in this logarithmic equation. So we're not going to use 1-to-1, but we can isolate this log, and I notice that the natural log is by itself on the left-hand side. So we're going to exponentiate both sides, but the thing is we have to exponentiate them with a base of e. Because we are taking a natural log, it means that I have to use base e to get these to cancel using our inverse property. So we get left with this square root of x minus 8 equals e to the 5th, and from here we're just going to take into account normal solving techniques. So squaring our square root to get rid of the square root here and get the x on the outside, e to the 5 to the 2 is e to the 5 times 2 is e to the 10, and then the only thing we'd have to left to do here is add the 8. And so we actually get an exact value of e to the 10 plus 8. I'm going to box that, and then I'm going to make sure at least that I check this out here. If I did second ln, or e to the power of 10, and we add 8 to that, we get a value of 22034.4658. So about 22304. Let's try that again. 034 point, and we got about 4658. So about 4658. So this is approximately our solution here. And it'd be easier for us to plug that back in and check. Okay. Now, letters F and G. Here's where it gets really interesting. You notice that I do, as a matter of fact, have more than one log, and that they are both base 2. But if I were to try to subtract this log over to the right-hand side, what I would get is log base 2 of x equals 5 minus log base 2 of 3. So no matter how hard I try, I can't use 1-to-1 because it's not a log equals a log. It's like a log equals a log that has a negative in front of it and has this 5 being added to it. 1-to-1's not going to work here. So this goes back to what I had written on that table above us here as my note. We're going to scroll back up here, but whoops. Let's try this. It is this. We may need to use the properties of logarithms to condense logs if necessary. So if our job is to get the log by itself and there is more than one log in a sum or a difference, then we're going to condense this into a single log base 2, and we'll just have to multiply x times 3 on the inside. This would be the same thing. So in this instance, you notice that I do have the log by itself. Now I can just kind of wrap parentheses around both sides and say, well, those are both the exponents to a base of 2. We'll exponentiate both sides with a base of 2. So we get 3x equals 2 to the 5th. And because I think that that is entirely reasonable, we could say 2 to the 5th is 32. We get x equals 32 thirds. And again, you know what, I can check this, but what I'm really checking for instantly is just if I put 32 thirds back in here for x, am I taking the log of a negative number? And I wouldn't be, because 32 thirds is positive. So this last example we look at is going to involve the same technique. I certainly have 2 common logs, but because of this 3 on the right, I'm not going to be able to pop one of my logs over the other side and use 1-to-1. So we're going to go ahead and condense these. It is a sum of 2 logs with base 10, so we can write a single common log base 10 there and multiply what was on the inside. So we're going to have to take x times x minus 1, and in this case, this is still equal to 3. Now that we have a single log on the left and it's by itself, that is, we don't have a coefficient, okay, we don't have any loose constants being added or subtracted to this thing, we're going to go ahead and I'll wrap these up, and we can use brackets since I've got a lot of parentheses on the left there. And we're going to exponentiate both sides with the base of 10. So what this does is on the left it produces just this xx minus 1, and on the right we have 10 to the power of 3. And so really, if we're going to solve this, this is some exponential equation, and what I end up having to do is solve this equation right here that I've set equal to 0. So what I know is I'm going to get two solutions. And I also know that I can't think of two numbers that multiply out to be 100 that add up to be -1. So if I'm going to solve something like this, I have options. I think that the option that I'm probably going to go to is to use my quadratic formula. And so since it's a quadratic and set equal to 0, we're going to do -b over 2a, our square root of b squared minus 4ac to dig out our solutions here. But our b value is -1 in this quadratic polynomial. Our a value is +1, so 1 and 1, and then our c value was -100. So we end up with this 1 plus or minus all over 2, square root of 1. I count a negative and a negative here gives me a positive, and 4 times, I suppose, 100 would be 400. So our two solutions here are going to be 1 plus or minus the square root of 401 all over 2. I actually want to make sure that I take a moment to get some decimals on these. So with respect to what we have, I suppose I have 1. We're going to put this in parentheses. All in parentheses, 1 plus the square root of 401 in parentheses, divided by 2. And then I'm going to hit second enter just to pull up what I just typed in, and I'm going to go back and change my plus to a subtraction. So I get these two values here, and what I notice is one of them's positive, one of them's negative. So I want you to list them both algebraically. 10.5125, so approximately 10.5125. But we also approximately got -9.5125, so about -9.5125. With respect to both of our solutions here, I'll box them both, but I noticed that if I were to put in -9.5125 back in for x right here, what's inside my log would be negative. Even if I put it right here, it would be negative. And so this negative answer is actually extraneous. And when you can check it out, plug in 10.5125. But what I want you to notice at least instantly is when you plug that 10.5125 in for these x's, you'd be taking the logs of positive things. And so we don't have to trash that answer unless it doesn't give us a solution. Okay. So solving exponential and logarithmic equations, in large part, we're going to check for 1-to-1. But if you can't use 1-to-1, we're either going to isolate the base of the exponent or isolate the log and use our inverse properties to undo it and solve it. Okay? Cheers.